Hello friends, we are studying digital signal processing and today we are going to understand the concept of Z transform in abstract. Lot of things are there in Z transform, but what is required to understand the discrete time sequences and the discrete time LTI systems? So first of all, x of n is a discrete time sequence over length minus infinity to plus infinity. It's a range of discrete time. Time index is n here. And we have a discrete time LTI system. Say y of n is equal to 5 x of n plus 1 plus x of n minus 1 plus x of n. If you see this, the output of the system depends upon the present and the future inputs. Okay. So how Z transform help to understand the discrete time sequences and discrete time LTI systems? First of all, Z transform converts this time domain to Z domain. It converts the discrete time sequence or discrete time signal. Wherever we want to use Z transform for analysis purpose, it converts time domain representation to Z domain representation. And how it helps? There is no need of calculus. No need of calculus for doing this. Simply we need only a basic algebra. By using basic algebra, we can understand, we can perform the analysis of discrete time systems and discrete time systems. Okay, and we can find the stability of a system. We can find the stability of discrete time LTI systems, linear time invariant systems. By using Z transform, we can design digital filters. So Z transform helps to design of digital filters. So we are going to study later the design of various digital filters using the Z transform. Okay, so let us see what is the Z transform equation. X of n we have defined over minus infinity to plus infinity. Z transform is an operator. If I write like this, Z transform of x of n. So Z transform is denoted by x of z or x of z. It's uppercase x and it's uppercase z. So it is x of z is equal to sum of n is equal to, the range of n is minus infinity to plus infinity, x of n 0 raised to minus n. So this is the equation of Z transform. This is called bilateral Z transform. The sequence x of n is two-sided, left side of 0 and right side of 0. We can write the same equation for right-sided sequence also. We can write like this. So it is 0 to infinity x of n 0 raised to minus 1. Okay. So this is for, you can say, for causal sequence. And this is for non-causal sequence. We can also write for anti-causal sequence. Only the summation limit will change. Okay. So what is z in this equation? So z is equal to r e raised to j omega. So we have to understand the meaning of this z, r equal to e raised to j omega. If it is z equal to r e raised to j omega, it clearly shows that, so x of z, whatever the calculation we are obtaining by performing this operation of summation, product of the summation, x of z is a complex term. complex term, okay, where z is a complex variable, you can say. Z is a complex variable term. Okay, so let us spend 1 minute understanding z equal to r e raised to j omega. So it is z is equal to r e raised to j omega. So here omega is so angle. Actually, it is the angular frequency. We can say angle, or say let us say angular frequency. It's more appropriate in radians. Okay. So what is omega? Omega is angular frequency. It is in radians. Let us say omega is 0. Omega is say so pi by 2. Omega is pi. Omega is 3 pi by 2. And omega is 2 pi. So if you substitute these values, okay, you will find the value of z rotates around a circle, okay, and we need z plane for that. To represent this term z is equal to r e raised to j omega, we need z plane. So z domain and we have z plane. So here this is the real part of z and this axis is imaginary part of z. So how we are getting this real part of z and imaginary part of z? If you substitute here z is equal to r e raised to j omega is exponential term. We can represent the same term in trigonometric form, cos of omega minus j sine of omega. So this term, okay, this same equation is represented in the form of trigonometric form. So this presence of j indicates that the z is a complex term. And x of z we are getting is the complex figure. And for that, z transform uses the z plane. So this is the z plane. Okay, and this is the unit circle. This term is very useful in defining the z transform and understanding any discrete time sequence and discrete time system. So it is unit circle. Okay, and the value of r is calculated by using the magnitude of z term. Okay, when we take the magnitude of this, we'll get the z term, and same way we can obtain the e raised to j omega also. Real part and imaginary part of this term will provide us the magnitudes of these terms. Okay, so z term is denoted by a point here at this. So this is the r, so radius of the circle, and here z is equal to e raised to j omega. It is r e raised to j omega. Okay, r is the distance from this point. Okay, now where is the omega? Omega is an angle. So this is the angle. Here this makes the angle omega. Okay, as we have written 0 when e raised to j omega. Okay, omega is 0. What we'll get? We'll get here 1. So here it is 1. Okay, we can say, we can write this in a more simple term. So it is e raised to j omega is cos omega minus j sine omega. If you substitute the values of omega, it's cos of 0 minus j sine of 0. So cos of 0 is 1 minus 0, it is 1. So e raised to j omega, in this case we are getting 1 here. Okay, this portion is 1 because we are getting because of change in omega. So this values of omega changes from this, and here we'll get, so it's a minus j. If you substitute, it's a cos pi by 2. So cos pi by 2 is 90 degree and it's 0, and we'll get minus j here, and here we'll get minus 1. We can calculate these values, and here, sorry, it is plus j, and minus j we get here, minus j. So this is called negative part, negative of imaginary part of z, and this is real part which is negative, real part of z which is negative, real part of z which is positive, and imaginary part of z positive part, and negative imaginary part of z. Okay, so this is the z plane. By using this z plane, we can find the region of convergence of z transform and the stability of discrete time system. Okay, so Z transform help to design the digital filters by providing the equation in polynomial. We can plot the poles and zeros on this Z plane, and we can predict many characteristics of digital filters, whether it is stable or unstable. Okay, so let us discuss about the region of convergence of Z transform. ROC. So it is called the region of convergence of x of z. What is x of z? X of z is the z transform of given sequence or given system. So region of convergence is the region for which the x of z converges. We can write in the simple terms, the ROC, x of z is ROC is the region for which x of z, or we can say the region of convergence for which x of z attains, or in more appropriate term we can write like this, x of z. Region of convergence of x of z is the set of all values of z for which x of z attains the final value. ROC is a region of convergence. Region of convergence of x of z. Okay, so region of convergence of x of z is, okay, ROC of x of z is the set of values of z, is the set of values of z for which x of z attains finite value. Very important concept. When we solve the equation for x of z and we get an answer, and in that answer when we put the values of z such that we can obtain a value, finite value from that, those values of z are called the region of convergence, and that is located on the z plane. Okay, so we are going to solve example, and there you will understand what is region of convergence and what are the values for which the x of z attains the finite values. So x of z equation, we have x of z is equal to sum of x of n over this limit x of n z raised to minus n. Okay, and we have seen the polar form of this is z is equal to r e raised to j omega. Okay, where r is equal to magnitude of z and omega is equal to angle of z. Okay, so in this way we can proceed and solve some examples on z transform. Let us solve examples on Z transform and find its region of convergence. We have to find the region of convergence. The first sequence, so arrow indicates n equal to 0. So this is the right-sided sequence. So this is the causal sequence. And here n equal to 0, so left side. It means it is the anti-causal sequence. And this sequence arrow indicates here n equal to 0, so left side of 0 and right side of 0. So this is the two-sided sequence. And these sequences are finite sequences. Okay, so fixed number of x of n's are given at different indices and we can count it. These are finite sequences, and these three, okay, this one is again the causal, so anti-causal, and it is two-sided, but these are infinite sequences. As a raised to n is given, b raised to n is given, these are the infinite sequences. We can find the z transform of these sequences too. Z transform is applicable to find the z transform of finite sequences, infinite sequences, and discrete time systems also. We can design the digital filters using this. And these are the perfect examples to understand the region of convergence or different types of sequences. Let us proceed with the first one. So we have x of n. The first example is x of n is equal to 2, 1, 2 and 3. So we have z transform of x of n is x of z is equal to sum or minus infinity to plus infinity x of n z raised to minus 1. Actually it is the power series. Z transform is the power series. Using this power series we can obtain the z domain representation of the sequence. So what is given? So here arrow is indicated. Arrow means 0. So for x of 0 is given, so 2. So first example, let us write each and everything so that you can understand how to solve the z transform of this given sequence. X of 0 is 2, x of 1 is 1, x of 2 is 2, and x of 3 is 3. So these are the magnitudes of given sequences. And this inside, this indicates the n index. Okay, so we have this. Let us substitute the value of x of n, these values with this. So this index, what is the range of this index? N is equal to, so it starts with 0, 1, 2 and 3. So this n will vary according to this. It will start from 0, 1 to 3. It's going to right side. So x of z is equal to x of 0, so z raised to minus 0. As I said, it is going to the right side. X of z, z raised to minus 0 plus x of 1, z raised to minus 1 plus x of 2. So this figure we are writing here, so it is value of n. So x of 3 and z raised to minus 3. So here, so finite sequence and n finishes n equal to 3. So 4 samples, 1, 2, 3 and 4 we have. So x of 0 is 2. So it's 2, z raised to 0 plus x of n is 1. So it is 1, z raised to minus 1. X of 2 is 2, z raised to minus 2. And x of 3 is 3. So it is 3, z raised to minus 3. Let us make it simple. Z raised to 0. Actually a raised to 0 is 1. Therefore it is 2 simply. So 2. So 1 over z. So it is minus. So it will be, if you invert this, we'll get 1 by z plus, so 2 by z square plus 3 by z cube. Okay. Now we are interested in region of convergence of x of z. Now what happens? See, if you take z equal to 0, let us put z equal to 0 in this equation. What will happen? So x of z is equal to 2 plus 1 by 0 plus 1 by 0 plus, sorry, 2 by 0, 3 by 0. So it is 2 plus infinity. So it is equal to infinity. So x of z goes to infinity at z equal to 0. If magnitude of z is 0, it means x of z, the region of convergence, is going to infinity. So this x of z does not exist for z equal to 0. Except z equal to 0, if you put any value here, you will get finite answer. If you take 1, so it's a 2 plus 1 over 1, so 2 and 3, you will get some finite value. Okay. So let us locate this region of convergence. See, it is real part of z and it is imaginary part of z. Now, what is ROC of this? So RBC exists. ROC is region for which it attains the finite value. And if you substitute z equal to 0, you are getting infinite value. Means region of convergence is the region of convergence except mod of z equal to 0. Okay. Means here z equal to 0, x of z don't have convergence. For any value of z except equal to 0, it exists. Means except this, it has whole region is the region of convergence. So we can show like this, the region of convergence for this we can show by using this color. So this is the region of convergence for given x of z. Except this, so the line will not enter this 0. So this is this area. Okay, so it is going to the infinity. Okay, so this is the region of convergence for given obtained x of z. Let us solve second example. Now here the signal is anti-causal, so left-sided sequence. So let us find z transform of this. X of z we have, so summation or minus infinity to plus infinity x of n z raised to minus 1. So in first example we have given how to substitute the values of x of n from this given sequence. So directly I am writing the values x of, so here n equal to 0, therefore What is the range of n? So it is n equal to, so 0, minus 1, minus 2 and minus 3. So n, range of n is minus 3 to 0. So we are getting 4 samples. So it is x of minus 3. It will start at x of n equal to minus 3. So this is z raised to minus of minus 3. Okay. This is the difference between the causal and anticausal sequence when we substitute in the z transform equation. So it is x of minus 2. So z raised to minus of minus 2. So it is minus of minus 2. Plus x of minus 1, z raised to minus of minus 1, and plus x of 0, so it is z raised to 0. So this is going to be x of minus 3, z raised to plus 3, x of 2, z square, plus x of minus 1, z raised to plus 1, and plus x of 0. Z raised to 0 is 1 anyhow. So it is x of minus 3. What is value of x of minus 3? Is 2. So z cube plus 1 z square plus 2 z raised to 1 plus x of 0 is 2 and z raised to 0 is 1. So we are getting this equation. Now we have this x of z, z transform of x of n. So it is 2 z cube plus z square plus 2z plus 2. Now substitute, put z equal to 0 in this equation, x of z. So x of z will become, so 2, so 0 plus 0 plus 0 plus 2. You are getting finite value. So for z equal to 0, we are getting finite value of x of z. Means x of z converges for z equal to 0 in this case. Now if you substitute z equal to infinity, what you will get? You will get infinity. Okay. So x of z will be infinity for if magnitude of z is infinity. Means region of convergence is present for z equal to 0 but not present for z magnitude of z equal to infinity. The region of convergence is so it will include the unit circle. So here it is going to infinity. So z equal to mod of z equal to infinity. So less than this value, the region of convergence exists. So this is the region of convergence for anticausal sequence. Okay. So real part of z and imaginary part of z. Okay. And this is the ROC for mod of z equal to 0. It is present at z equal to 0 also, and it is extended up to z equal to infinity. Okay, it's not going beyond that. So let us solve the third example. Now this sequence is two-sided sequence. It is present. So it is n equal to 0, left side of 0 and right side of 0. The previous example, the first example was right-sided, second example was left-sided, but this example is two-sided. Let us check the region of convergence of this. So we have x of z. Now we can solve directly. X of z is equal to summation or the one length. This is the first equation of z transform. So it is n. Now what is the range of n here? So n is, so it is two samples left of 0. So it is minus 2, minus 1, 0, 1, 2, 3. So it is here 0, 1, 2 and 3. So this is the length of index n. So this is the length for this n, we have this length. Okay, let us proceed. So it is x of, you see this and write according to that. So x of minus 2, z raised to minus of minus 2 plus x of minus 1, z raised to minus of minus 1 plus x of 0, z raised to 0, x of 1, z raised to 1 plus x of 2, z raised to 2 plus x of 3 and z raised to 3. So let us substitute the amplitude of this x of n for the specific index. X of minus 2 is 1, so it's z square plus 2 z raised to 1 plus 0 z raised to 0. So it is minus term, so it is minus of minus 2, so minus amplitude is minus 2, so it is z raised to 1. X of 1 is minus 2, so this term, so x of 1 is minus 2, it is z raised to 0 plus x of 2, 1, 2 is 3, so it is 3 z raised to 2 plus 1 z cube, so it is 1 z square plus it is minus, okay, it is minus, it's minus, it's minus. So x of 0 is 0, so it is 2 z raised to minus 1. Actually it is not 0, it is minus 1. So 1 z square, 2z plus, so it is 0, actually no need to write 0, so minus 2 z raised to minus 1 plus 3 z raised to minus 2 plus z raised to minus 3. Now we have x of z transform of x of n. Let us substitute values z equal to 0 and see the region of convergence. If you substitute z equal to 0 in this equation, so what you will get? See, it is z, 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 z and z. You will get n. What you will get? You will get x of z equal to 0. So you will not get finite value. You are getting 0. So x of z is not finite for mod of z equal to 0. Means the ROC is not present for magnitude of z at 0. Is that clear? ROC does not exist for this value. What is ROC? Region of convergence is the set of values of z for which the x of z is not infinite or it is finite. The values of z should be such that we should get the finite value of x of z. Then it is said that the x of z converges. Okay. Now let us substitute z equal to infinity in this. What you will get? You will get infinity. Okay. So x of z is infinite for this, means for mod of z equal to infinity, okay, ROC does not exist. That is the conclusion of this. Okay, we can show except these points the complete region is region of convergence of x of z. So this region, so it is the representation of this, that here is the infinity. It is not actually infinity, but we are taking this point as an infinity, z equal to infinity. Here the ROC does not exist at z equal to infinity, and here at z equal to 0 ROC does not exist. So we can show this. So mod of z equal to 0. The remaining portion, the ROC is present. So this region is the region of convergence. So here the line should not penetrate this small circle. Okay, it's not unit circle. This point represent z equal to 0. I have shown somewhat larger, but it is close to 0. It is the 0 point, and thus is the imaginary part of z representation of the axis, the real part of z. As it is the complex term, we have to write here. So this is the z plane and region of convergence of x of z. Okay, let us proceed. Next example. The given sequence is infinite sequence as value of n goes 0 to infinity. Okay, therefore it is a infinite sequence. Let us obtain the z transform of this infinite sequence. So we have x of z equation summation over minus infinity to plus infinity x of n z raised to minus n. So let us substitute sum for the given summation range is x of n is a raised to n u of n. Now here u of n is present. So this is the u of n. So unit discrete. So this is discrete unit step sequence. What is the index for this unit step sequence? So we can show this unit step sequence as, so this is for the writing title. So here, so it is 0, it is 1, it is 1, 2 and so on. It is up to infinity. So it is plus n, and for rest of the things it is 0. So this is the, so this unit step function, unit step sequence is present, and n for this is 0 to infinity. So let us use this. We have multiplied this a raised to n using u of n. Ultimately the summation range for a raised to n will be 0 to infinity because of multiplication of this with unit step sequence. So this will be, summation will change because of unit step sequence. So it is 0 to infinity a raised to n z raised to, sorry, here I forgot to write z raised to minus n. So z raised to minus n. We can simplify this as it is a z raised to minus 1 raised to n. Now we have to use one relation. So we have one relation, sum of 0 to infinity, sum of a raised to n over 0 to infinity is equal to, so like a raised to 0, a raised to 0 will be 1, okay, a raised to 0, a raised to 1 plus a raised to 3 plus a raised to 4 plus so on a raised to n. So it will be like this. So it is 1 plus a1 plus, sorry, it is 2 here, 2, 3 and so on. So it's 2, 3 and so on up to an, and this is equal to 1 minus a. So this is the relation we have to use, and we have to simplify our equation. So what we'll get? We'll get x of z equal to, okay, once again I'm writing x of z equal to equation. So it is x of z we have obtained. So it is 0 to infinity a z raised to minus 1 raised to n. This is our equation. By using this relation we can write this as 1 minus, So here in place of a we have az raised to minus 1. So as it is, this term will appear here, az raised to minus 1. We can simplify this further as 1 minus a over z. Okay, same thing, we have written positive index here by inverting it. Now this term will help to understand the region of convergence of x of z. Okay, I'm taking it separate. So x of z, we have now x of z is equal to 1 over 1 minus a over z. So this is the term we have. Now when this term will become infinite, so it depends upon the values of a and the values of set of values of z. Okay, so the value of z should be greater than this a. If value of z is smaller than this, this will be infinity. Very simple. So mod of z should be greater than a. Mod of a. Then the region of convergence exists. Okay, a is some value. Okay, so it will start from 0 and it will make a circle, and beyond that region of convergence of x of z exists. Let us draw the region of convergence of this equation. So real part of z, imaginary part of z, so minus imaginary part and minus real part. So this is a here. So this portion is a in this case. The value of z should be such that it should be greater than magnitude of a. Okay, it means the region of convergence will exist more than this. Okay, not exactly this, so it can be any higher value than this. The given sequence converges, so this is the region of convergence. Out of this unit circle. Okay, and we can show this as ROC for mod of z greater than mod of a is the region of convergence.